So, we have seen the theory of small reflections. Let us now consider a multi-section matching transformer. The figure shows a multi-section matching transformer, where we have capital N number of sections. Each section is having an electrical length theta, and the transmission line sections have impedances Z1, Z2 up to Zn, and this transformer is designed to match this load ZL to this transmission line having characteristic impedance Z0. Now, we introduce the partial reflection coefficients gamma 0, gamma 1, gamma 2, gamma n at these interfaces whenever there is a change in impedance, and gamma is the overall reflection coefficient. We can write gamma 0 equal to Z1 minus Z0 divided by Z1 plus Z0, and continuing in this manner, gamma n is equal to Zn plus 1 minus Zn divided by Zn plus 1 plus Zn, and finally, gamma capital N is ZL minus Z capital N divided by ZL plus Z capital N. Now, we assume that all Zns they increase or decrease monotonically, and ZL is real. So, that means this Z1, Z2, Zn all will increase either monotonically or decrease monotonically depending upon the values of Z0 and ZL. If we consider the theory of small reflections what we have discussed, we can write gamma, the overall reflection coefficient, as a function of theta as gamma naught plus gamma 1, this is the partial reflection coefficient, minus j e to the power minus j 2 theta plus gamma 2 e to the power minus j 4 theta and gamma capital N e to the power minus j 2 capital N theta. Further, we assume that the transformer be symmetrical. That means, what we mean is gamma naught is equal to gamma n. Please note that the impedance increase or decrease monotonically, but this impedance level, for example, Z1 and Z0 is selected in such a way that gamma naught becomes equal to gamma L, which is decided by ZL and Zn. So, if we assume this type of symmetry, then we can write gamma theta e to the power minus j n theta, gamma naught e to the power j n theta plus e to the power minus j n theta plus gamma 1 e to the power j n minus 2 theta plus e to the power minus j n minus 2 theta plus and so on. Now, capital N, it can be even. In that case, the last term will be gamma capital N by 2. If capital N is odd, the last term will be gamma capital N minus 1 by 2 e to the power j theta plus e to the power minus j theta. And these two equations can be written in terms of Fourier cosine series in theta as gamma as a function of theta is equal to 2 e to the power minus j n theta, gamma naught cos n theta, gamma 1 cos n minus 2 theta, and finally half gamma n by 2 for n even, and gamma as a function of theta equal to 2 e to the power minus j capital N theta gamma naught cos n theta plus gamma 1 cos n minus 2 theta and finally gamma n minus 1 by 2 cos theta when capital N is odd. So, we have discussed how we can find out the reflection coefficient for a multi-section transformer in terms of the electrical length of the individual section theta, and now let us see how we can design a binomial multi-section matching transformer. Now, the passband response of a binomial matching transformer for a given number of section is as flat as possible near the design frequency. So, that is why it is also called maximally flat response, and in this type of design what we do, the reflection coefficient, that means gamma theta, can be represented as gamma theta is equal to a 1 plus e to the power minus j 2 theta raised to the power n. So, we already have a Fourier expansion of gamma theta. So, we are trying to now map this response. So, if we write modulus of gamma theta, then we can write it is mod of a 2 cos theta mod raised to the power n, and this can be written as modulus of gamma theta is equal to 2 to the power n modulus of a modulus of cos theta raised to the power n. Now, we can see that modulus of gamma theta equal to 0 for theta equal to pi by 2, and nth derivative d n modulus gamma theta d theta n equal to 0 at theta equal to pi by 2 for n equal to 1, 2, capital N minus 1, and we find that theta equal to pi by 2 corresponds to L is equal to lambda by 4. That means, now we are considering a binomial multi-section transformer where each element, each transmission line sections are lambda by 4 or quarter wave long at the design frequency. Now, if you consider f equal to 0, then theta becomes 0 and all sections have 0 electrical length. What does it mean? That the line is directly connected to the load impedance, and therefore, from the expression of gamma theta evaluated at theta equal to 0, we can write 2 to the power n a and equal to z l minus z 0 divided by z l plus z 0, and the constant a can be determined as a equal to 2 to the power minus n z l minus z 0 divided by z l plus z 0. Please note that we have already mentioned that this matching transformer we are considering for a real load Z L. Now, we can expand this expression 1 plus e to the power minus j 2 theta raised to the power n using binomial expansion, and we can write gamma theta is equal to a sum of n equal to 0 to capital N n C n e to the power minus j 2 n theta, where we are defining n C n is factorial n divided by factorial capital N minus n into factorial small n. And what we can do, as we said that now we equate it to the response of a multi-section transformer, which is given by gamma naught plus gamma 1 e to the power minus j 2 theta plus gamma 2 e to the power minus j 4 theta, and what we can do, we can equate on a term by term basis. Then we find A NCN is equal to gamma n. Now, we have gamma n is z n plus 1 minus z n divided by z n plus 1 plus z n. What we can do, as we have said that the change in characteristic impedance from one section to the next section is very small. So, we can use this equation log of x is approximately equal to 2 x minus 1 divided by x plus 1 when x is close to unity. So, our z n plus 1 by z n is close to unity, and using this expression for log x, we can write gamma n to be equal to half log z n plus 1 divided by z n. Therefore, log z n plus 1 by z n, we can now substitute gamma n, which is 2 s n c n, and then substitute the value of A, which is 2 to the power minus n z l minus z 0 divided by z l plus z 0, what we have derived earlier. And then we can further simplify it into log of z n plus 1 by z n is approximately 2 to the power minus n n c n log z l by z naught. Now, this gives us a relationship where we can calculate z n, z small n iteratively, where we can calculate z small n recursively. So, we start with z naught. Please note that right hand side is known. So, we can calculate z 1. Then once z 1 is known, we can calculate z 2, and in that way we can keep calculating till z capital N. We can find the characteristic impedance of all the lambda by 4 sections that are used in that multi-section transformer design. We can also have an estimate of the bandwidth that we can have for this type of a multi-section quarter wave matching transformer. Let gamma m be the maximum value of the reflection coefficient that we can tolerate over the pass band. Then we can write gamma m is equal to 2 to the power n mod a cos raised to the power n theta m, and from there we can find out theta m corresponding to that value of gamma m, and we know that the reflection coefficient will increase on either side of the design frequency, for which we have theta is equal to pi by 2. So, we take this theta m value less than pi by 2, and now we can write fractional bandwidth delta f by f naught is equal to 2 times f naught minus f m divided by f naught. F m is that frequency at which the reflection coefficient becomes gamma m, and that can be written as 2 4 by pi cos inverse half gamma m divided by modulus of a raised to the power 1 by n. Here this n is the number of sections that are present in the transformer. Let us now move on to another method of impedance matching, the impedance matching with tapered lines. Here the impedance capital Z of the line varies with distance z, and we are showing this in this figure. So, at small z is equal to 0, we have capital Z, Z is equal to Z naught, and over a length L, this impedance capital Z changes to ZL. Now, what we can do? We can consider this tapered line being made up of incremental line lengths delta Z as shown. So, here you can see we have an incremental length delta Z. On the left hand side we have impedance capital Z, and over this length small delta Z we assume the impedance to be capital Z plus delta capital Z, and therefore, at this interface the reflection coefficient, partial reflection coefficient delta gamma can be written as Z plus delta Z minus Z divided by Z plus delta Z plus Z. Now, in the denominator we neglect this delta Z term, and we can write the approximate expression as delta Z by 2 Z. Now, when this delta Z tends to 0, this length tends to 0, we can write delta gamma as d gamma. So, d gamma becomes equal to d of capital Z divided by 2 Z, and this can be written in this form, half d of log capital Z by Z naught divided by d Z into d Z. This can be seen from here, because d of log of capital Z by Z naught by d Z into d Z is essentially d of capital Z by capital Z. Next, what we do? Now, we have this expression, we apply again the theory of small reflection. Now, the total reflection coefficient at Z is equal to 0, that means at the input of the tapered line, is given by gamma is equal to half integration 0 to L e to the power minus 2 j beta Z. This is the phase shift, and d of log of capital Z by Z naught by d Z into d Z. Now, this gives the overall reflection coefficient at the input of the tapered line. Please note that if we know Z Z, that means the impedance variation as a function of distance Z, we can find gamma. So, let us see how we can do that. So, we consider a very commonly used taper, which is an exponential taper. Here capital Z as a function of distance Z is given by Z naught e to the power alpha Z for 0 less than Z and Z less than capital L. Now, since this capital Z at Z is equal to L is ZL, and therefore, we can find alpha to be equal to 1 by L log of ZL by Z naught. And we have the expression for gamma. Now, in this expression we have we can now substitute Z equal to Z naught e to the power alpha z. So, this Z naught and this Z naught will get cancelled, we will be left with log of e to the power alpha z, and this can be log of e to the power alpha z will give alpha z. When differentiated, we will be left with alpha, and integration of 0 to capital L e to the power minus 2 j beta z dz. Now, we substitute the expression for alpha from 1 by L log of capital Z L by Z naught, and then carry out this integration, then we get the final expression for the reflection coefficient gamma to be half log of Z L by Z naught e to the power minus j beta L sin beta L by beta L. The magnitude of reflection coefficient is plotted in this figure as a function of L by lambda, and we can see that as L by lambda increases, the peak value of mod gamma decreases, and the length should be greater than lambda by 2, at least lambda by 2, to minimize mismatch at low frequency. This is because this exponential taper is designed to operate for a broad band of frequencies, and we want the reflection coefficient to be less than some specified value. Say if it is to be less than 0.1 even at the lowest operating frequency, then we should have L by lambda at that frequency greater than 0.5. So, the peak values of mod gamma decrease with L, and length should be greater than lambda by 2 to minimize mismatch at low frequency. And it is to be noted that we have considered beta independent of z, that means it is not a function of z, and such assumptions are valid for TEM lines. There are other forms of tapers like triangular tapers, and the impedance matching can be performed with such tapers. This actually brings to the end of this module. In this module, we have discussed in detail some of the impedance matching techniques, starting with the lumped elements. Then we have seen matching with stubs. We have seen how impedance matching can be done using a quarter wave transformer. We have seen how we can design multi-section quarter wave transformer, and finally, we have seen how we can use taper line for doing impedance matching. Our next module will be on microwave resonators, where we will study first series and parallel resonant circuits. We will have discussion on Q factor, bandwidth, and then we will discuss on transmission line resonators as well as waveguide resonators.